welcome to What's in My Data? Field analysis for the advanced engineer. Now, a presentation on Splunk doesn't feel quite right without a forward-looking statement, so here's mine, which has absolutely nothing to do with the stock market or the company Splunk itself, but does free me from any liability for socks unintentionally blown off. Who am I? My name is Ryan Wood. I've been a daily Splunk user for 9 years now. I'm currently working delivering professional services at GuidePoint Security with a background spanning several major industries before coming on board here. I started off my Splunk career as a network ops analyst where I grew to really appreciate useful tools built in the front end of Splunk that made my day-to-day easier. Since this presentation is aimed at a technical audience, I believe it's best to show up front why this may be relevant to you. Well, if you've ever found yourself struggling to pick one field over the other, or looking for an easier way to track down that specific conf file where a field is defined, or maybe you just like learning some SPL trickery, this presentation's for you. So, what are the utilities that we'll be covering today to kind of help answer these questions? Derivation of fields in your data, where they're defined, where they're coming from, where they exist. This includes calculated fields, field aliases, props and transforms extractions, and automatic lookups. We're going to cover building a summarization of data contents with top values of each field output in a readable, searchable format. But maybe summarizing aggregated data isn't quite detailed enough. How about that same summarization, but broken out by a group by, which enables us to easily compare multiple data sets with each other. And, you know, I bet we can go even deeper. How about that summarization with multiple group bys? During the course of this presentation, we'll be walking through the underlying query logic of the summary utilities shown here with some bonuses, and best of all, they're already available for you to download on GitHub. But first, a disclaimer. These references were written with a goal of being readable, searchable, and non-version specific. As a result, you're not going to see the most concise and efficient SPL possible. And you shouldn't assume that this is a representation of best practice, whatever that means in SPL development terms. I've tested these in a range of environments, but as always, your mileage may vary, and I make no promises that a future version of Splunk won't break them. My goal with this presentation is to give Splunkers in the position that I was many years ago something to serve as a learning reference and to build off of. I encourage you to take these examples and run with them, and then share what you build with me, and we'll call it even. Okay, with that done, let's get into the good stuff. Before we dive too deep, and in the spirit of a simple solution being a good one, if you don't need an expansive field summarization with coverage rates and all that fluff, then this may be a better path for you. Here, we're using a wildcard stats function that will run across all available fields to compile the first value of each. Then we use transpose to convert the stats output into a 2-column view for a simple and effective insight into what the current available fields are, along with a sample value of what they contain. On the right side, you see a macro version of this query, which I use most often when I'm writing complex SPL and I need to confirm exactly what I've got to work with in the middle of my bigger search query. Now be aware, this is returning the first value for each field, not necessarily the values in the first event or in the first row. This can be confusing if your data contains empty strings or only white space as a field value, as Splunk considers that to be not null. Additionally, this will only return the first value of any multi-value fields. So there are some caveats, but if you only need that 10,000-foot view, we'll say 1,000-foot view, then great, right? If this is enough, awesome. But if it's not, well, let's take the plunge and see what else we can do. So let's frame the problem. show of virtual hands that I have no way of actually seeing from here in the past, but who here has found themselves spending way too much time trying to grasp what the content of some specific subset of your data is? The fundamentals one solutions often simply don't scale with deeper development. And if you don't have some sense of what you're looking for, are kind of inadequate. You end up with a situation where you have millions of events with thousands of fields and hundreds of unique fields and values in each of those fields, and tabling it out only gets you a frozen browser or what might as well be an infinite scroll bar. So what can we do? Well, we use the field summary command. Field summary is a core Splunk command that essentially creates a summarized report of meta characteristics and top values that are currently available in the dataset at the time you call the command. The number of top values returned is dictated by the max vals argument, and naturally, the overall compute required by the command increases alongside that number and alongside the size of the dataset being summarized. Well, that sounds ideal, right? And perfect solution. Well, let's take a look at the default output. So we've got distinct counts and numeric counts and max and min and standard deviation and a not so easy to read array of JSON containing the top values for each field. Now, this is definitely a step in the right direction, but there's a lot we could still do to make that output more useful. And thus, we come to the core of this presentation and my solution to this problem. Easy peasy, right? Well, this monster of a search may seem like a lot, but we're going to walk through this entire query together, step by step. And by the end, you'll hopefully see this as less of a monster and more of a friendly pet. Now, that last screenshot and the following slides will not include the full comment blocks embedded in the references as they exist on GitHub. But each of these field summary utilities is segmented into individual purpose-driven components that are marked with a start and an end comment to help clarify what each part of the query is doing. That, additionally, listed on the right here are two lines of note that I want to call out on their own. The first is the minimum number of events expressed as a percentage of the total that a field must be not null to show in our final results. The second is the actual field summary command itself's arguments. I mentioned this earlier, but the max vals argument is directly tied to the compute necessary to complete the summarization. So it's almost assuredly a bad idea to leave it at the default value of 100. You don't want to run a top 100 values function across hundreds of fields spanning millions of events, because not only the compute required is going to be way higher than you really want to use, but because listing that many results in our final output would make it impossible to get the value that we're actually looking to gain. So what are these component groups? First, and I have to stress that this step can take many forms, which we're going to cover. We fetch our data and run our field summary. Second, we take the default output of the field summary command and consolidate it down through some enrichment and filtering to the specific data points that we care the most about. Third, we transform the values JSON that we saw earlier into a more useful format by turning it into a multi-value field. Fourth, and this one's pretty cool, we dynamically align the columns of that multi-value field we created to be more easily readable. And then last, we aggregate the result rows to reduce the overall amount of output that we need to dig through to reach the conclusions that we're looking for. Now, this core framework that we're walking through is the no group by field summary example, which is only one of the three types that I showed earlier. The other two utilize the same component structure beyond the first step where you fetch your data with some specific lines that also have to be updated. those lines are notated here. And essentially the logic is, if you're passing a group by, you have to make sure to pass that group by to the appropriate line so that the intended output and behavior remains consistent. I mentioned the other primary difference being the first step, where we fetch our data and run our field summary. Well, the addition of group by functionality means that we need to iteratively run our field summary, which we accomplish by using the map command. In the top example, we pass a set of wildcard strings to the primary map search, which will group our field summary results by the wildcard values passed as input. I wrote this example this way as a dual demonstration of how you can utilize make results to parse a list of values on the fly. The bottom example uses t-stats to generate a set of index, source type, and source values that are then passed as filters into our primary map search, and that will serve as the group by for our field summary output. As a note, you make sure to adjust your max searches value for the map command as needed to fit the number of unique combinations in your initial output. It can be higher, but if it's lower than the actual number of unique combinations, you're going to get cut off halfway through trying to build your summary. All right, now that we've covered the overview of the components at a high level, and let's start walking through the individual query steps. First things first, we got to get our data. Now, field summary runs on the data available at time of command call, meaning that the input in this case can be anything you want. Raw events, lookup tables, data models, other searches, any form that Splunk data takes can be used as input for this case and then summarized. Now, once we've got our data, next, we run our field summary. As you saw in the previous slides, the format that the field summary takes will vary in two primary ways. One, the direct field summary on the data available at time of call. This is just a straight up call to the command, right? This uses the data already available in the search to run a summary of what's available at that point. Now, the second is field summary via map, which we saw some examples of. This is the core of how we separate the resulting information into group by categories, giving an effective view into our data to help us really understand how each subset of information differs. Once our field summary is run, we end up back at the default output. Now, this is just a reminder so that we know where we're building from as we walk through the query. All right, so now that we've got the default output, it is time to clean it up. So first, and the way that we're going to progress through this is essentially each section of the query that we talk about will be highlighted line by line or a few lines at a time. So first, we're going to aggregate the isExact and the distinct count fields together, since they're innately connected due to the limitations of the field summary command itself. From the documentation, it notes that if the number of values of the field returned exceeds the max vals argument, then field summary will stop retaining all of the values and make an approximation of the distinct count instead of providing an exact one. So to minimize or to combine two different columns of information into one, we create a new one. Then we use event stats to take the max of the count. Then we use event stats to take the max of the count field across the data set per group by to establish a total that we can then use to create a percentage of how many events contain a value in that field. So because field summary doesn't inherently do a count of the initial input data, we use a stopgap in this form by leveraging event stats across the overall data set, or in the case of running group bys per group by, to establish what the max value of that is. Because for our purposes of identifying coverage percentages, that might as well be the number of events. I've never been in a situation where the number calculated this way was inaccurate, but that's sort of where we're coming from with this. Next, we filter to only fields that exist in greater than 10% of the data. Now, I wrote this way to show you how you can utilize a trim function, either right or left trim, to filter or manipulate or work with values that have strings already attached to them, such as percentages or dollar amounts. Now, as you can see from the table, the processed field is the only one with less than a 10% coverage, so it gets dropped from our results. Now, the count field in this context and coming out of the field summary is based on how many events that were scanned, or result rows in the case of running it on already formulated results, exist where each given field is not null. So in this case, most of the time, we only care about fields that exist in a minimum percentage, right? If something only exists in 1% or 2% of the overall events that we're looking at, it's a lot more cumbersome for me to include that in that final output. Now you can reverse this and actually look at just the fields that are a lower percentage if that's kind of what you're after. But yeah, so last for this section, we drop any fields that are unnecessary for our goal. If you want to keep any of these fields, simply modify this line along with the final table command later in the query, and those fields will show up in your final output. We've now achieved taking the default field summary output, which contained a lot of data and that was not really relevant to our interests, and we've honed it down to the specific elements that we care the most about. All right, so now's when the fun starts. So the next component step is to modify this values JSON array so that we can work with it a lot easier. We start by using the spath command to extract the value and the count properties from each JSON object into dedicated fields, value strings and value counts. Now, I apologize up front because the name of the column is values. There's going to be some terminology here, so I'll try to be as clear as I can. You can see the extracted multi-value fields containing each one of these elements in our data into their own dedicated columns. If you notice, each one of those multi-value fields retains the ordering of the JSON array, which is important because we're actually going to preserve this ordering all the way through to the final result output. Since this is a data summary, the contents of the values field could be anything. In order to help ensure that we retain what's what and to demonstrate a fun way to combine the mv join and split commands, we wrap each value string in double quotes without having to expand the multi-value field itself. Here, because mv join is inside of the split function context, we're able to use a triple colon delimiter to concatenate each value together, also adding our double quotes, and then convert it back to the multi-value field by using that triple colon split. I chose triple colons because that sequence is typically rare, at least in my experience, and unlikely to be found in our value strings natively. You can combine embedded functions in this way to accomplish a great many things. Now, a word of warning though, the behavior of the embedded functions is dependent on the core Splunk search code. I've had situations where behavior of a specific line that had 6 levels of functions all passing upward to get to the outermost layer, right, changes its actual behavior between versions of Splunk, just due to the way that the engine that handles all of those sequences was updated. It's better, in my opinion, to have multiple eval lines than to consolidate everything down to a single line that's more likely to break. As a note, for Splunk 8 and above, you could also accomplish this by using the mvmap function, which, contrary to essentially every example I found generally available, does not, in fact, only work on numeric fields. Who'd have guessed? Next, since we know that the value strings and value counts fields will always have the same number of multi-value items since we're extracting them from the same source, that JSON array. We can use the mvzip function to stitch them together into a new values field that replaces that old JSON. Once we've done that, we can drop each of the individual fields as we no longer need them. And just like that, we've now got a much cleaner looking field detailing the top values found for each field listed in descending order. Now, that's great, but those staggered numbers are still a little bit difficult to read. So let's do something about it. The next session starts off with aligning the columns in this multi-value to just make it cleaner to read. So we start this column alignment section. Man, what a mouthful. We start the column alignment section by expanding the newly created values field, then use rex to extract the value string and value count back out into their own distinct fields. It's important to note here that it is necessary to first combine the strings, values, and string values and count values together into a single multi-value field in the previous steps. We had to stitch them together into a single multi-value field in order to perform a clean expansion in this manner. While at first it seems roundabout, if we had attempted to expand in this manner while the two existed as independent multi-value fields, upon running mvexpand on the first field, we would have the undesired effect of duplicating the other multi-value field across all of the expanded rows. If we had then run mvexpand on the second field, the resulting duplication of the overall data set would result in both higher compute and higher difficulty consolidating our results afterwards. It's often convenient in Splunk terms to concatenate data together while passing it through a bottleneck transformation before separating it back out on the other side of that transformation. We've now, as you can see in this table here, achieved separating each unique field plus values combination into its own row without duplicating any of our data, where we have individual fields allowing us to work with the string and count values separately, which leads us directly to our next step. Now that we've separated out the value string, we use event stats to determine the maximum length of each field's value string across the data set, adding our group by if appropriate, and then use that to calculate the difference between the length of each individual value string in that group and the maximum difference, adding 4 spaces as a standard padding. As you can see here, the maximum length plus 4 space characters is established for each field in that in the max field value len field. Then we calculate white space insert amount dynamically based on the maximum length of any of the values in that group by. We could not have accomplished this by simply expanding. We could not have accomplished this as simply without first expanding the multi-value field. I'm sure many of you can guess where this is going next. Now that we have the dynamically determined white space insert amount to adjust each row, it's time to actually transform the individual value strings and individual value counts so that they align. We do this by leveraging the substring function and concatenating the different segments together to form a new combined modified values multi-value field. Now note, for a reason beyond me, this alignment will not appear correctly if wrap results is not enabled in your format options. If there happens to be any Splunk developers in the audience that know why, I'd love to understand. Separately to those same developers, please don't break this behavior, as it's the only way I've been able to figure out how to pass a dynamic length of white space as a concatenation argument. That's a feature. We utilize an overly long whitespace argument passed to the substring function to take a smaller portion of that long whitespace block and append it onto the value string, followed by our standard colon, and then finally the value count. The result is a new values field containing the combination of those fields, now adjusted to align with each other across each group by group. So in this case, you can see that the PID field now has all of its values aligned, even though the individual values shown in the PID field are variable length. Last, we must consolidate our rows back together while maintaining that descending order of count values. The stats values function natively. So the stats values function natively sorts based on lexicographic ordering, deduplicating all of the found values in the data for the field you specify it against into a single multi-value. Since we want to retain our sorting by established counts from most to least, which the left side table shows is already sorted correctly after we did our expansion, we leverage the list function instead of the values function. Since we're also using a wildcard stats values call to handle all of the other fields for ease of merging, it's necessary that we separately make an explicit stats values function call on our values field. I told you this terminology is confusing. You see this here notated as values. This must be separate to retain ordering. Essentially, the idea is that by explicitly calling out to the values field in this way, using the values function, we avoid the wildcard function at the end of the stats statement from overriding our list function at the beginning of the stats statement. Because we don't need this field, we immediately drop it afterwards. If you want to see this happening in action, just run this example and play with the stats outputs, and it'll become really apparent. But what we end up with is on the right here, a transformed set of values from, summary. This section is particularly useful as you can adapt this method to a number of different outputs. The comparative readability between the left table and the right table speaks for itself, right? Having everything lined up in this way makes making conclusions at a glance a slam dunk. And honestly, it's proven to be useful in a number of different tables in dashboards, as well as alerts and reports. This is actually a callback to why I took the approach I did in separating each component section of the references in the way that I have. The goal there is to allow you to play with each individual section's options, removing and adding and changing the command structure to see exactly what it's doing. Now that we've aligned our values field and it looks nice and pretty, all that's left is to get the final output into the most concise, useful presentation that we can manage. Our last section is another effort at increasing readability. One of the problems with summarizing fields in a data set is that there are many, many fields which contain values that are entirely duplicative of each other. For example, field aliases will always be the same in 100% of events. So using 2 or more rows to represent each of those fields separately in our results makes it much more cumbersome to sift through. In this section, we use the MD5 hash function to create a checksum value, which is a concatenation of all of the data points outside of the field that we're looking to consolidate. In this case, that field is literally named field. It's important to note that we will need to add any group by fields to the checksum calculation if we don't want to unintentionally merge rows across our unique group by values. Also, the concatenation shown here in context of an eval will fail to generate a value if any of the fields included doesn't exist in the data. In this case, all of the fields that we're using were populated from the field summary command. They will always be present in 100% of the outputs coming from field summary, so that's not a concern. But if you have issues with this segment of the reference, ensure that this isn't unintentionally happening and that you haven't unintentionally dropped a field that is trying to be considered in your checksum evaluation. Last, I wanted to speak to the usefulness of this method more broadly. So outside of the context of just this field summarization and the way that we're using it here, utilizing hash functions off of concatenated fields is an extremely useful way to attach a unique ID to a row in a result set and can be leveraged in a lot of different ways inside Splunk to perform some really cool tricks. An example would be creating a hash that then serves as a unique database table ID, which you could put into a KV store. And then anytime a field outside of those unique values gets updated, that update is passed directly to the corresponding checksum. Something to think about. It's a great reference generally. All right, our next step. We then leverage event stats to pass the field names across rows identified as identical using checksum. So we generate our checksum value, which is the hash representing the combination of every field except the field itself, right? We then sort by our checksum value and then use stream stats to process through our data set, establishing a counter that resets each time the checksum value changes. So event stats here is used to pass separate rows into each other so that we are not losing any fields whenever we do our deduplication or our aggregation, which you can see in the table here. It doesn't merge any rows in which there are not full matches of this nature, which is an extreme benefit for reducing the number of results that we have to sift through. Stream stats is useful because it iteratively processes over the data set when we call it and can be used in this manner to create a running counter that then, in our last step, can be used to deduplicate. So we utilize the stream stats counter as a way to identify rows that are duplicates of each other, which is a better solution than something like stats first star is star or stats value star is star, because each of those will inherently affect our data and the final results in a way that is undesired. We use the where command to filter out any records where stream stats has identified multiple copies so that we're left with only the first row representing each unique checksum hash. This can take field summarization results from hundreds and hundreds of rows to dozens, and is really the last enhancement that we needed to gain insights at a glance without having to scroll through the same information over and over and over. It also has the secondary benefit of allowing you to see duplication of values across your data set in different fields, which becomes particularly useful when dealing with things like common information model, right? If two fields are expected to be duplicates in 100% of events, they should be lumped together in the final output. And if not, then there's at least a few events where that differentiation is causing them to result in two unique checksum values. This sort of approach is really fun to see where you can implement it in different ways, in different methods. And I really want to stress the usefulness of concatenating your fields together and using it as, or just generally using hash functions. It's a way to create a unique representation of some piece of your data. All right, with that, we've now walked through each of the components making up this summary utility. So we started with this monster of a query, right? And now we've actually walked through every single line in this query. And a lot of them, while it seems to be a lot, really aren't that complex when you look under the hood. First, we fetched our data and generated the default field summary output. Then we enriched and filtered that output. We transformed the generated JSON array into a multi-value field. We then modified the formatting of that multi-value field to align the columns. And then we aggregated any of our duplicate rows to decrease the overall number of results that we have to look through to gain value from our final result summary. This is more of just a text write-up of each of those individual component steps. Now that we've gone through each of the components making up the queries, let's review the output of those summary examples again with this added understanding. All of which are made available at the GitHub link in the bottom left of these slides. So field summary with no group by. This is our base, which can be run on any input data. The query for this is quite large, as you saw in the previous slides, but you can actually copy and append it beginning at the field summary point onto any input data that you want to summarize at any point in a query or a data set. This can be particularly useful when looking to validate query methodology to ensure that you're using the field that you intended to, and that there aren't any unexpected variances in your data that you may need to investigate to ensure that the query that you're developing is fully accurate. Next, we have a field summary with a single group by. In this case, it's actually a wildcard string filter on index. This method can be incredibly useful for combining separate data sets together and summarizing them in a logical group defined by you in your final summary output. Here we can see all of the indexes that begin with OSNix are all lumped together, and all of the indexes that begin with OSWin are lumped together. So if there's some common element that I really would expect to be present in 100% of data across all of those indexes, this is a way to check that. And last, a field summarization by index, source type, and source, which, this enables extreme insight into the contents of our data. It allows us to better identify what fields we want to use for development, as well as potential misconfigurations or configuration problems that become apparent at a glance when viewing at this level. Now, I know what you're thinking. Didn't he say scalable? Yeah, right. Run an open-ended map command in a 25 terabyte a day cluster and see how that goes. Map is expensive, and ideally we'd be able to get specific, and I agree. So I'm going to give you the tools that I use to take this solution to scale, and as a result, hereby refute all angry emails from your Splunk admins that they may want to send me. I apologize in advance. You should optimize the map searches if you're running into map limits, or if you have concerns about the overall size of the data you're running this on. The following two examples of doing that are not included in the default GitHub query references. They are listed on the README, but not baked in as part of the queries, but are necessary for scaling to large data sizes. Here we're using a case statement to create a field where we assign unique filter strings based on the data returned from our tstats search. You'll notice that my case statement has some conflicting logic. Because I already set a value where source matches XML win event log system, the earliest and latest assignment is only applied to XML win event log application. Make sure to check your logic before you run the fattest part of your search. Use multiple case statements if you need to, then leverage mv append and mv join to flatten those out before passing it into the primary map search. So how do we actually pass this defined filter into our primary map? Well, because map automatically wraps past values in a specific manner, we have to actually use an embedded subsearch to pass the true value back to the primary map search. If you weren't already aware, setting the output field of a subsearch to search, this terminology, setting the output field of a subsearch to search will pass the result directly to the outer query without modifying the string that you've created. This is a great way to dynamically reduce your search impact in many different scenarios, not only just for this or just for the map command. Now, what about limiting the overall number of events that we're considering? Well, we could use the head command. In this case, we're specifying the maximum number of events that we want to consider, passing the numeric value to the head command inside of the map search. Be careful of doing this. You can unintentionally skew your summary results by limiting the initial input events. So be sure you know what you're doing. Your creativity is ultimately the only limit when it comes to finding interesting, dynamic ways to restrict the map command in a way that ensures that it will complete in the time that it has allotted. I encourage you to explore different ways to define filter parameters to reduce the footprint of your summarization search and hone in more closely to the data that you really want to summarize. You can run blanket, unfiltered summarization searches on massive data sets. Sometimes that's what you need to do. But I recommend doing so outside of business hours and leveraging a lookup file as the output to call back to the results at a later point. If you run into limitations around the map command itself that you can't overcome in this manner, or if it's too unwieldy to try to build that many factors in, you can run individual summary searches, output them into lookups, which then you can stitch together for a significantly less overall impact. All right, so we've got a field summary by index, source type, source. I've got 395 fields. It took 2 hours, 4 hours, 10 hours to complete the summarization across my 100 terabytes of Cisco network data. Be wary of running expensive summarization searches repeatedly. So how else can we get the most bang for our buck? Loadjob. Loadjob, or outputting the results to a lookup, can be a great solution for reusing the same results output in different ways to gain the most out of that spent compute. With the move towards workload-based pricing, this becomes more important than ever. I highly recommend getting your development staff and advanced users familiar with using lookups and load jobs in this way. This isn't included in the slide deck, but a tip for the audience that's listening. You can actually append a .gz onto your .csv output lookup designation to preserve all of the same CSV lookup functionality while also taking advantage of gzip compression. This can be massively beneficial for your bundle size and is something that can help get your admins on your side when it comes to helping out with this. So, load job calls out to a search ID. How do we get that search ID? The easiest way to do so is utilizing the job inspector or the add info commands, which I've given an example of here in a macroable version to access the search ID of the job. One of the favorite things that's been a development is the enrichment of alert output in recent year or so. With the move towards risk-based alerting, there's been a significant increase with the need for context. And so one of my own personal favorite habits now is to include this add info set of 3 lines, the add info on the right side, the add info rename, and then the for each statement as a macro reference that then I append onto every one of my alerts. What that does is allow me to better understand what was the context of when that alert actually fired, right? What was the search time range it was running on? What was the search ID of that job? All of that being included in the alert output itself is extremely beneficial to your analysts, to your engineers, to everyone that ever may need to go track down that specific circumstance. So let's see an example of load job in action. Here we see the output of our query feeding into the row consolidation component. That was our last component where we used our checksum MD5 hash to consolidate our data together, which this is, again, demonstrating the benefits of that. So in our results, we took 4 rows And because all 4 of these rows had the exact same values across them, we're able to merge them down into a single one. Now, not only was I able to merge them down, I didn't have to go back to the raw data to do this next part of the query. I could use loadjob. I grab the search ID, I call to it in my search, and then perform the query that I want to run. Now, as a reminder, search artifacts do not replicate across search head clusters by default. I don't recommend that you turn that on based on Splunk's recommendations so far. This does mean that if you are not on the same search head that ran that original search job, you will not be able to call to that search ID using loadjob. The easiest way to get around this is to output that original search to a lookup file. You can specify that lookup file to not replicate down to the indexers if you only care about making it available on the search heads. And then you can call back to that lookup file from your other search head to fetch the results. All right, last thing for loadjob, I wanted to share a few simple ways to gain more value out of a single set of summarization results across multiple group bys. On the left, we pass a search for any results where the field contains name. This can be a great way to identify misconfigurations in your field extractions and to help hone in on what fields you may want to use. On the right, I'm looking for any result rows that contain the string windows in the values for that field. This is ultimately limited by the max vowels used when you compiled this data, but these are examples of how you can output your summarization and then leverage loadjob to get multiple different insights off of that same single summarization. No extra compute, no need to rerun the search. So I know we've covered a lot, and I know it's been a lot of content. Say I used my field summarization search to identify something abnormal about my field extractions, or I see something there that's unexpected and I want to track it down. Well, typically, the process of finding which specific conf file is contributing which field can be quite troublesome and time-consuming. How can we improve that? Using the REST API from front-end SPL, we can generate a consolidated view of what fields are defined, where they're defined, and turn that whole investigative process into just a few clicks. In this utility query, we can see multiple really useful columns, such as which file it came from, the stanza that the specific configuration exists under, the actual configuration value itself, and additional conf specific properties aggregated into a single unified field. This slide is from a .conf 2019 presentation that was also given at a bunch of previous years that originally helped get me started way back in the day. And shout out to Kyle Smith. The REST command executes an API call to the internal Splunk endpoint and returns data to the search window as results. This does require GET privileges for REST functionality, and the output will be limited to the individual user's capabilities. This presentation isn't going to dive into the technical side of the REST command, but I encourage you to go explore the Splunk documentation for available REST endpoints and try the command out yourself. This is a summary. This is summary information on the field Derivations utility, which leverages a series of REST command calls combined with some SPL trickery to merge all those varied REST outputs into something that makes more sense. There's a set of common fields that are standard across these different endpoints, but there's plenty that are unique that we still care about. So how do we deal with the infinite scroll? Well, let's consolidate. We won't be covering the query components in a similar manner to the summarization, but there are a few pieces that I want to walk through. The main callouts that I wanted to note here are the 2 sections highlighted in each subsearch. First, highlighted in orange, the for each line shows a way to combine differing fields across a data set into a single aggregated column that makes it much easier to consolidate the final view. The basic logic is if the field that it's iterating on is null, create the new multi-value field. If it's not null. If it's not null, create the new multi-value field. If the multi-value field already exists, append the current field's information to it. And if the field in question is null, then retain the multi-value information compiled to that point. For each, executes iteratively on your data set in a vaguely similar manner to stream stats, but I encourage you to go play with the command itself. It's kind of difficult to explain easily. But second, highlighted in green here, inside each sub-search context, we create a data source field that serves as an identifier for the final output on where that information came from. This is the way that you're able to track down the data source, even in the aggregated final view. This is an example of using the union command instead of a series of appends. However, union creates a series of append searches in the background if transforming commands are used. So this is more for elegance than any actual performance improvement. Great, we're done now, right? All the tools and the possibilities, it's overwhelming. Well, not yet. I've got one more in the bag for you as a bonus. Yes, that's right. There is an easy way to see every field configured in every data model in your instance, along with the inheritance information related to each data set inside that data model. We aren't going to go through the query components, but you can also find this reference at the GitHub link along with everything else. The SPL itself is pretty compact, so let's take a quick look. So, local information queries on a single instance, such as a host querying information about itself that doesn't require it to reach out to any external sources, are very minimally impactful resource-wise. So we're able to crank that max searches setting all the way up and get all that sweet, sweet data model configuration information in one go. The same notes apply for load job and lookups. It's best when you don't need to run this search repeatedly, just to avoid the load on the dispatch reaper to clean up all those individual search jobs that were created via the map command. And with that, we made it. If you enjoyed this talk and are potentially interested in taking your Splunk solutions to the next level through professional services, please reach out using the contact information at the end of this presentation, and I'll help get you in touch with the right people. For those fellow engineers, feel free to say hello at a future.conf and know that I am personally very much looking forward to see what all of you are able to build in the future. Last but not least, some additional reading. If you haven't gone and viewed these presentations, I highly recommend doing so. This is the content that helped me take my first steps years and years and years ago into the world of what SPL can do. To close, I wanted to offer a sincere thank you to all of these presenters and community leaders that put the massive amount of time and dedication necessary into creating these presentations and comprehensive references. I would not have been able to become the engineer that I am today without your hard work, and I'm truly appreciative. Thank you very much for attending. If you have any questions, feel free to throw them out in the chat. I'll be available to help answer. You can reach out via the Splunk user group Slack at the Wood Ranger. You can also email me at ryan.wood@guidepointsecurity.com. Have a wonderful day, take care, and happy Splunking.